Hi ma'am, I am Madhu from CSCB section. Today I am going to discuss about single source shortest path using greedy method. Introduction to shortest paths. Shortest paths problem are fundamental in graph theory. They involve finding the minimum distance between nodes in a weighted graph. Various algorithms exist to solve these problems with greedy methods being one of the most efficient. Understanding graphs. A graph consists of vertices and edges. Weighted graphs assign a cost for distance to each edge. The shortest path problem seeks to minimize the total weight from a source node to other nodes. We can see the picture weighted graph. Single source shortest path problem. The single source shortest path problem focuses on finding path from one source node. The goal is to determine the shortest path to all other nodes in the graph. This problem is crucially in numerous applications like GPS navigation and network routing. Greedy algorithms overview. Greedy algorithms build up a solution piece by piece. They make locally optimal choices at each step with the hope of finding a global optimum. Dijkstra's algorithm is a well-known greedy method for solving the SSP problems. Dijkstra's algorithm introduction. Dijkstra's algorithm is designed for graphs with non-negative edge weights. It systematically explores the nearest unvisited vertex to the source. The algorithm guarantees the shortest path from the source or to all other nodes. We can see the step 1 and we can understand. Algorithm steps overview. The algorithm maintains a priority queue of vertices based on their tentative distances. It repeatedly selects the vertex with the smallest tentative distance. The distance to adjacent vertices are updated accordingly. Initialization. Start by setting the tentative distance of the source node to 0. All other nodes are initialized to infinity, representing unknown distances. A priority queue is used to efficiently retrieve the next node to process. Iterative process. The algorithm iteratively selects the vertex with the smallest distance. Once a vertex is processed, it is marked as visited. The process continues until all reachable vertices are visited. Updating tentative distances. For each unvisited neighbor of the current vertex, the distance is updated if a shorter path is found. This involves comparing the current known distance and the newly calculated distance. If the new distance is smaller, it replaces the current distance in the priority queue. Handling ties. In case of ties, the algorithm can choose arbitrarily among those nodes. This does not affect the correctness but can influence performance. Efficient implementations can mitigate the impact of ties through careful queue management. Termination condition. The algorithm terminates when all reachable nodes have been processed. The priority queue becomes empty, indicating no more nodes to explore. At this point, the shortest path to each node is finalized. Time complexity. The time complexity of Dijkstra's algorithm depends on the data structure used. With a priority queue implemented as a binary heap, it runs in big O of v plus e log v. This makes it efficient for sparse graphs where e is much less than v square. Space complexity. The space complexity is primarily determined by the storage of the graph. It requires big O of v space for the distance and predecessor arrays. Additional space is needed for the priority queue, resulting in an overall big O of v complexity. Limitations of Dijkstra's algorithm. Dijkstra's algorithm can handle graphs with negative edge weights. The presence of negative weights can lead it to incorrect path calculations. Alternative algorithm like the Bellman-Ford algorithm are required in such cases. Application of single source shortest paths. Single source shortest path solutions are widely used in navigation system for route optimizations. They are also utilized in network routing protocols to determine optimal paths. Other applications include urban planning and logistics management. Comparison with other algorithms. Bellman-Ford and Floyd-Warshall are alternatives to Dijkstra's algorithm. While Bellman-Ford handles negative weights, it is slower than Dijkstra's. Floyd-Warshall computes shortest path between all pair of vertices, but less efficient for SSSP. Visual example. A visual representation can help in understanding Dijkstra's algorithm. Diagrams show the step-by-step selection and distance updates. These visuals aid in grasping the underlying mechanics of the algorithm. Implementing in programming. Dijkstra's algorithm can be implemented in various programming languages. Most implementation utilize priority queues for efficiency. Pseudocode can provide a clear understanding of the algorithm's flow. Summary of key points. Dijkstra's algorithm is a powerful greedy method for SSSP in non-negative weighted graphs. It efficiently minimizes distances using a systematic approach. Understanding its mechanics and limitations is crucial for its correct application. We can see the Dijkstra's algorithm in the picture. Conclusion and question and answer. The single source shortest path problem is a vital area of study in computer science. Greedy algorithms like Dijkstra's provide efficient solution to this problem. Question and discussions are welcome to deepen understanding and clarify concepts. Feel free to modify any of the content or structure as needed. Thank you.